for everyone. So I'd like to thank the people who did the work that I'm going to tell you about today. My graduate students, Rick Dorn, Scott Carnahan, where Scott, there he is, Yunhua Chen, Mike Hanrahan, and undergrad researcher Matt Ryan primarily did the work I'm going to talk about today, and I'll try to highlight their contributions throughout the talk. I'd also like to thank our collaborators, Javier Vela, Wenyu Wong, and some of the work was done in collaboration with Mark Prusky's group, Fred Perra, Takeshi Kobayashi, and most of the work was supported by the US Department of Energy. So what we work on in my lab are developing DNP and fast magic angle spinning NMR methods to enhance NMR sensitivity and enable us to do more challenging 2D or multi-dimensional NMR experiments that can provide more structural information. And we apply these techniques to look at problems in materials characterization and characterization of solid pharmaceuticals. But I'm just going to focus on these two areas today. So one of the things we're interested in as part of our work that's funded by DOE is using and developing NMR to look at next generation energy materials. So materials such as nanoparticles, perovskites, 2D materials, metal organic frameworks. These are the materials that are really posed to address the problems that we have in energy conversion and storage, separation of chemicals, and catalysis. So if we think about the typical design cycle that material scientists and chemists undergo when they're making these materials, they're going to synthesize something, measure properties, perhaps perform some calculation, and then characterize things and try to go through this rational design cycle. And I would often argue that characterization is the bottleneck here, because when we think about these materials, in many cases, the activity is going to be controlled by the structure of their surfaces or interfaces, and those are difficult to characterize. Oftentimes there's structural or substitutional disorder, and many times we have dilute defects or dopants or active sites. And by virtue of the fact that they're dilute, that makes them difficult to see or observe. So NMR is really an ideal technique that can address these challenges in characterization. So the first class of materials I'm going to tell you about are two-dimensional materials. There's lots of interest in these materials, mainly stimulated by the synthesis and characterization of graphene, which was awarded the Nobel Prize in the mid-2000s. So there's lots of different types of 2D materials out there, and they go from insulators to semiconductors to superconductors, and they have lots of potential applications: catalysis, photodetectors, transistors, supercapacitors, etc. One material that we got interested in studying was hexagonal boron nitride. This has a very similar structure to graphene or graphite, where you're going to have this honeycomb structure. In this case, rather than having carbon atoms, we have these alternating boron and nitrogen atoms that make up the honeycomb. The reason we got interested in studying this material is because we actually have a collaborator, Yves Herman's group at Madison, Wisconsin, and they are using hexagonal boron nitride as a catalyst for the oxidative dehydrogenation of alkanes to alkenes. So one of the fundamental questions that we came across when we were studying this material is that nobody really knows what the edge or termination of this material is. What is the molecular structure of the edges? And so if you start doing some digging in the literature, there's been some nice high resolution TEM studies where they've deposited single layers of boron nitride onto pristine polished metal surfaces. And you can pick out zigzag edges and armchair edges. So the zigzag would be this edge termination. This would be the armchair. But then you start reading some of the computational chemistry literature and some of the catalysis literature. And there's this hypothesis that there's a lot of oxidation of the edges that may be occurring under ambient conditions and maybe under some of the higher pressure and higher temperature catalytic conditions that these materials are used under. So that was really the fundamental question we wanted to address in this study. So the way we made the samples for this study is we took bulk hexagonal boron nitride, which you can just buy from any commercial chemical vendor. You just placed it in a liquid. You can use organic solvents, or in our case, we just use water. If you take your boron nitride and you put it in water and then you sonicate it, you'll actually partially exfoliate the sheets into smaller nano sheets. If you centrifuge the sonicated boron nitride nanosheets down and just collect the small nanosheets from the supernatant, these sheets are colloidally stable. So this solution will stay cloudy, or suspension will stay cloudy for weeks or months if you leave it, and there's no surfactants added here. So just looking at some SEM images, this is the boron nitride before we take it through the liquid exfoliation process. You can see sheets that are on the order of 500 nanometers in diameter, a couple hundred nanometers thick. After we do the exfoliation, we get much smaller nanosheets. We reduce diameters down to, say, between 50 and 200 nanometers. And if we look at the thickness of the sheets, they're around 20 layers of boron nitride thick. Now, we did some basic FTIR characterization. We can see some stretching signals possibly associated with hydroxyl groups and maybe amine groups. And we can also see some BO stretching frequencies. So that tells us the edges are likely partially oxidized during the course of this exfoliation. Okay, so if we want to do NMR to look at the edges of these materials, there's a problem we have to address. So the first problem we have is that the edge atoms, if that's what we're interested in looking at, they make up a very small fraction of the sample. So this is a 10 nanometer by 10 nanometer HBN sheet that I made. It's got about 3,900 atoms. About 346 of those atoms are going to be found on the edges, so 8% of the atoms are edge atoms. What this means is if we wanted to do a hypothetical NMR experiment where we would only see the NMR signals from those atoms that sit on the edges, we're going to have 12 times lower sensitivity, which is going to translate to a 144-fold increase in the length of our NMR experiment. Now, if we look at our TM image here of the exfoliated nanosheets, we actually have sheets that are more like 100 nanometers by 100 nanometers. So if you repeat that calculation, only about 0.9% of the atoms are going to be found on the edge of the sheet. So you're going to have 110 times lower sensitivity and 12,000 times longer NMR experiments if you do an edge selective NMR experiment. So really we have two problems, sensitivity and selectivity. And we can address both of these problems using the dynamic nuclear polarization surface enhanced NMR spectroscopy approach, or the DNP sense approach. So this was the approach that was developed, demonstrated by Lesage, Copperet, Emsley, and Bodenhausen in 2010. So the way that this approach works, or DNP sense experiment works, is we impregnate our exfoliated hexagonal boron nitride sheets with a biradical polarizing agent. In this case, it's going to be TechPol dissolved in tetrachloroethane. This is going to put radicals on the surface and edges of these sheets. And so if we zoom in here on one of the edges of these sheets, we'll have the polarizing agent in close proximity to the edges. When we do DNP, we're going to irradiate our polarizing agent with microwaves. That's going to cause polarization transfer to some proton spins that are nearby to the radicals. And then proton spin diffusion will mix that proton polarization evenly throughout the sample. So that's going to polarize both the proton spins of the solvent and the edges. And then we can do a cross-polarization transfer to selectively observe the nuclear spins associated with the edge or surface of the material. So this is the DNP-enhanced nitrogen-15 solid-state NMR spectrum of the exfoliated hexagonal boron nitride. This is natural abundance nitrogen-15, so the DNP was really critical here. We had DNP enhancements of about 200 for this material with TechPol, so that corresponds to over a 50-fold improvement in sensitivity. It took about 18 hours to acquire this spectrum, and so this is a nice example for Bob. I know he likes to put up examples like this. So without DNP, this would have taken about 4 years of signal averaging to acquire. So if we look at the spectrum, we can see 4 different isotropic chemical shifts. This peak at about negative 282 ppm. This is the known chemical shift of the nitrogen in the bulk of the hexagonal boron nitride. So to help us interpret that spectrum and understand what those different peaks come from, my student Rick Dorn, who led this work on the hexagonal boron nitride, he made plane wave DFT models of the edge terminations of the hexagonal boron nitride nanosheets. So he made a model where we have these zigzag edge terminations where you have amine groups on one side, and then you have hydroxyl groups attached to boron atoms on the other side. And then he also has made this armchair edge termination model where you can have nitrogens that are terminated with amine groups, or you're going to have borons that are bonded to hydroxyl groups. So if we calculate the N15 chemical shifts using these two models, we can really accurately reproduce the observed chemical shifts. So we can see that the zigzag model gives us these bulk-like atoms. So these are going to be the nitrogen atoms that are the first layer in from the surface. Those are going to show up here. And when we look at the edge groups, the amine groups on the edges, that's predicted to be this peak that we see here. For the armchair edge termination, we also get good agreement with the experiment. The edge nitrogen atoms are predicted to occur here at a slightly different chemical shift from those of the zigzag. And then the bulk nitrogens, those ones that are the first layer in from the edges, those are predicted to occur there. So this nicely explains the nitrogen 15 NMR spectrum that we see. We also went one step further and did nitrogen 14 NMR. We did this using room temperature, fast magic angle spinning experiments. So this is a proton detected nitrogen 14 DHMQC spectrum, dipolar HMQC. So this is using techniques that were developed by Jae-Young Gan, Jeffrey Bodenhausen, Jean-Paul Amaru, and some of those people. So in this spectrum, we could get this in about 13 hours, and we can see two nitrogen NMR signals. I'll talk about those more in a second. In the HMQC experiment, we can easily vary the proton recoupling time and record a series of 1D HMQC spectra, and just monitoring the signal intensity. We can then simulate that in Simpson, and we can fit that to get a dipolar coupling constant out. And we see that the dipolar coupling constant that explains this NH HMQC buildup curve corresponds to an NH distance of about 1 angstrom. So that really does confirm that we have those amine groups on the edges of the sheets. We can also calculate the nitrogen 14 NMR spectra. Now the nitrogen 14 NMR spectra, the peak positions and shapes are going to be affected by or determined by both the chemical shift and the nitrogen 14 quadrupole parameters. And we can simulate both of those effects based upon the calculated values. And you can see that in some ways, the nitrogen 14 more nicely resolves the different edges, the armchair edge and the zigzag edge. Okay, what about boron? Boron 11 is also a really good nucleus for NMR spectroscopy. It's got a natural abundance of about 80%, pretty high Larmor frequency. It would be 128 megahertz on a 9.4 Tesla spectrometer. So if we just do a boron spin echo, we're mainly going to see the NMR signals from the boron atoms in the interior of the sheets, the bulk-like boron atoms, because that's going to make up 99% of the sample. And we get this characteristic second order magic angle spinning quadrupolar powder pattern here. And this matches what's been reported for boron nitride. The isotropic chemical shift is at about 30 ppm. That also matches the literature results. Okay, if we want to see the edges, we can just do a proton to boron cross-polarization experiment. This is done at room temperature because boron offers good NMR sensitivity. And so when we look at the cross-polarization spectrum, we can now see some new signals coming in. These new signals have lower isotropic chemical shifts between 25 and about 12 ppm, and those chemical shifts fit with what you would see for oxidized boron compounds. So if you look at boron oxide or boric acid, that's where these chemical shifts would come in there. So these are tentatively assigned to boron atoms that have hydroxyl groups attached, or on the armchair edges where we can have both bridging oxides and hydroxyl groups on the boron atoms. And we have DFT calculations that validate those assignments. Now, one important thing here is if we're looking at these edges that make up a very small fraction of the sample, when we do this cross-polarization experiment, we really want to confirm these are the actual edge signals and not just some trace impurity that's in the sample. You could easily imagine, for example, that 0.1% or 1% of your boron nitride that you buy from a commercial supplier might be contaminated by some oxide or hydroxide impurities. So the way that we can check that is with a DNP enhanced boron spin diffusion experiment. So here we use DNP to enhance the proton magnetization of the edge protons. We transfer that DNP enhanced boron magnetization to the edge borons using a cross-polarization step. And then we give it some time for spin diffusion and can watch the boron magnetization diffuse into the bulk if these are the edge sites. And that's exactly what we see happening. When we have a short spin diffusion time of 0.1 milliseconds, we more or less see that edge selective NMR spectrum. And then as we increase the spin diffusion delay, we can see the magnetization entering into the bulk and giving us those bulk-like NMR signals. Another 2D material that we got interested in looking at are these transition metal dichalcogenides. These are indirect semiconductors with very nice band gaps that match up well to the solar spectrum. They have a lot of applications as electrocatalysts, transistors, and in spintronics. What we got interested in looking at for these materials is we have a collaborator in the Ames lab, Victor Belema. He's a mechanochemist, so his group has been developing methods to synthesize mixed transition metal dichalcogenides. So for example, they'll take molybdenum sulfide and tungsten selenide, ball mill them to mix them together, and then they can thermally anneal them to get mixed chalcogenides. And this is one way that you can tune the properties of these materials, is by tuning the composition in this way. So we started by doing some selenium-77 solid-state NMR to see if we could follow the transformations of these compounds when you do the ball milling and annealing. So the structure of these materials is shown here. In these materials, each of the metal atoms, which is going to be tungsten or molybdenum, is coordinated by 6 selenium or sulfur atoms. And then each of the seleniums or sulfurs has a trigonal pyramidal geometry where you're going to have bonds to 3 metal atoms. So shown down here are the static selenium-77 solid-state NMR spectra, just taken at room temperature. These are acquired using CPMG pulse sequences. CPMG is very efficient here. We can acquire spin echoes for a couple seconds. You have very long T2s, and that gives you a nice sensitivity gain. And you need that because the T1 relaxation times for the selenium are very long. They're on the order of 1,000 seconds. But with CPMG, you only need between 24 and 72 scans, but this still translates to between 6 to 18 hours per sample to obtain a spectrum. Okay, what happens if we look at a ball milled sample? This is molybdenum sulfide selenide that was made by ball milling molybdenum sulfide and molybdenum selenide. As we maybe expect, we don't see much broadening of our selenium spectrum since we're just going to be substituting in some sulfides into the selenium positions. That maybe is going to have a minimal effect on the selenium NMR chemical shifts. Now, if we go to a ball milled sample made by combining molybdenum sulfide and tungsten selenide, we see some significant broadening of the selenium-77 chemical shifts. And what that's indicating is that in the ball milling process, you're already starting to get substitution of the molybdenum and tungsten, or mixing of those 2 metals with one another. And so the fact that you now have some seleniums that are going to be bonded to both molybdenum and tungsten is giving you intermediate chemical shifts that are in between those of the 2 pure phases. Now, if we do the annealing, we don't see much difference in the spectrum. So this would maybe suggest that this cartoon picture here that they had originally developed, our collaborators had originally developed, is not quite accurate. There seems to be more mixing of the metals just during the mechanochemical step, even prior to the thermal annealing. Now, some of these spectra are rather broad, and we'd like to try and get high resolution spectra to give us a more accurate picture of the metal distribution during the milling step. And so we tried to do some MAS experiments to get the resolution up. So this is shown for the tungsten selenide here. So we can get that static spectrum in about 11 hours with CPMG. We can also do CPMG acquisition under MAS conditions, and we can obtain a magic angle spinning spectrum in about 14 hours. The long experiment times required for room temperature NMR prompted us to try DNP. So we just took the tungsten selenide, impregnated it with TechPol TCE, and did some DNP experiments. We got proton enhancements of over 200, and we estimate that the selenium cross-polarization DNP enhancements are greater than 20. So this means we can now get a magic angle spinning spectrum in about 15 minutes rather than 14 hours. Now, one interesting observation here, if we actually carefully look at the peak positions that we see in our CP-CPMG spectrum, they don't actually match up well with what we see at room temperature. If we do the pulse cooling experiment recently discussed by Emsley, and Snedis talked about this in a nice lecture in one of the early DNP webinars, where you give time for selenium spin diffusion to occur, we actually see a second set of selenium peaks that match up with the bulk selenium emerging. So what we think is happening here is these peaks that we see in the normal cross-polarization experiment are either from exfoliated sheets that have partially dissolved in the tetrachloroethane, or what can also happen is the solvent molecules can actually intercalate in between the sheets, and this would give you more efficient cross-polarization, and proton spin diffusion would let you see those types of species. Then when we go to the pulse cooling, we're actually maybe able to polarize the bulk-like or aggregated sheets and see the selenium-77 NMR signals. Now, coming to the mixed samples, we actually wanted to get the magic angle spinning spectra of these mixed samples here. Unfortunately, when we try and do both room temperature magic angle spinning with CPMG detection or DNP, we can't get any spectra. And the reason for this is because the milled samples appear to have high concentrations of unpaired electrons, and these are likely a result of the mechanochemical milling actually breaking chemical bonds and leading to dangling bonds that you then have unpaired electrons that become part of the sheets. So if we look at the milled sample of tungsten molybdenum sulfide selenide formed by milling tungsten selenide and molybdenum sulfide, we see this very broad EPR signal that's over 2,000 Gauss across, and we estimate the unpaired radical concentration is about 70 millimolar. If we look at the sample after annealing does remove some of those unpaired electron spins, but you still have a concentration of about 9 millimolar. So when we try and do DNP, we don't get any DNP enhancement from either of these samples. It seems like those unpaired electrons that are created during the milling process just react with and reduce or oxidize the DNP polarizing agents, and that's what stops DNP from working. At least it's one of the reasons why DNP doesn't work on those mixed systems. For the last bit of the talk, I'm going to talk about nanoparticles now. I don't know, Kong, should we stop here or should I just keep going?
Oh, it's up to you. What do you want?
I'll keep going, I guess,
Yep.
and we can just do questions at the end.
Perfect.
So we're also interested in studying semiconductor nanoparticles. These have lots of potential applications in light emission, display technology, photovoltaics, biological imaging. What's really important for semiconductor nanoparticles is understanding the surface chemistry. So you can prepare them with a number of different surface ligands, and the identity and types of surface ligands that you prepare them with are very important. What you really need to avoid having are undercoordinated surface atoms, because when you get these undercoordinated surface atoms, they act as optical traps that ruin the emission and absorption properties of your nanoparticles. So understanding and controlling the surface chemistry is very important if you want to get high-performing semiconductor nanoparticles. So there's been a lot of work done by conventional NMR to look at conventional solid-state NMR to look at nanoparticles. I'm going to skip over that for the sake of time and just focus on the DNP. In 2015, when I was a postdoc with Linden's group, we did this nice study with, in collaboration with Maxim Kovalenko and Christophe Copperet, where we came up with this way to do DNP on semiconductor nanoparticles. So the procedure we came up with is you take your semiconductor nanoparticles, which you usually have as a stable colloidal solution in an organic solvent. You trap the nanoparticles in mesoporous silica, and you add your polarizing agent. And the reason we need to do this is because the nanoparticles in the polarizing agent will then become trapped in the pores of the silica together. If you just try to add your polarizing agent to the nanoparticle solution and freeze it, what ends up happening is the nanoparticles will precipitate out as the solution cools down and freezes, and you'll end up getting phase segregation between the nanoparticles and the radicals. So by doing this trick with silica, you can prevent that phase segregation. This allows you to get pretty good DNP enhancements. So we have an enhancement of about 40, which we can measure from the carbon NMR signals of the ligands that cap the CAD sulfide nanoparticles. And then we can obtain a cadmium NMR spectrum in about 8 minutes. And for this study, we use CAD sulfide nanoparticles. And I'll talk more about what this cadmium-113 NMR spectrum means in a little bit. Okay, one of the problems though with this strategy is that silica is actually not a great material for DNP. So what I mean by that is it has unfavorable dielectric or optical properties for DNP. So what we showed in this 2014 paper when I was a postdoc in Linden's lab is that if you use materials or fill your rotor with materials that have a higher real dielectric constant, you tend to get better coupling of the microwaves into the DNP rotor, and that translates to higher DNP enhancements. And so you can see if you do a DNP experiment on silica, just impregnated with TechPol TCE, we tend to get enhancements of about 100. And we think part of the reason for that is because silica doesn't have favorable dielectric properties. It's lossy in the microwave region and it has a low real dielectric constant. So the idea we had was if we have to put in a material to disperse our nanoparticles to do the DNP experiment, let's at least put in something that has good properties for DNP. So we screened a couple materials. We tried alpha alumina, which is actually sapphire, and hexagonal boron nitride. So we observed when we use hexagonal boron nitride, just impregnate it with TechPol TCE solution, we can get DNP enhancements of about 360. And if you go look at the dielectric properties of this material, you'll see it has a high dielectric constant. So if we just switch the material from mesoporous silica to hexagonal boron nitride that we're using to disperse these nanoparticles, we can triple the DNP enhancements for the nanoparticles, and this corresponds to a doubling in the absolute NMR sensitivity. So that's pretty good. One problem though, if you look at this cartoon, it kind of highlights what the issue is. We're interested in studying the nanoparticles, and most of our rotor volume is going to be occupied by solvent and the boron nitride that we're using to disperse the nanoparticles. The way we can get around this is we can precipitate our nanoparticles as powdered aggregates. We can then mechanically mix it with the hexagonal boron nitride, or alternatively, you can just take your nanoparticle solution, put it onto the hexagonal boron nitride, let the organic solvent evaporate off, then you can impregnate it with a small volume of the TechPol TCE solution. So now we're going to have aggregated nanoparticles that are going to be kind of mixed with the hexagonal boron nitride. What this does is it really gets the nanoparticle concentration up. So we lose a bit of DNP enhancement because now we have some aggregation of the nanoparticles, but the increase in concentration more than makes up for that, and you get a large gain in the absolute sensitivity. We can get a factor 9 improvement in the absolute sensitivity on our cadmium NMR experiments compared to the original formulation strategy. So if we look at these, the DNP enhanced cadmium-113 NMR spectrum, there's 3 different signals we see. This signal at 50 ppm, that's the cadmium signals from the bulk-like cadmium atoms that are going to be coordinated by 4 sulfurs. Those are going to be found in the core of the nanoparticle. We have these surface cadmium atoms. They come in with enhanced intensity because this is a cross-polarization spectrum. So those are going to be the cadmium atoms that are coordinated by carboxylate ligands. You're going to have some CH2 groups on those ligands that can provide the proton polarization to the cadmium spins. And then we have this third signal, which we know is an oxide impurity or byproduct of the nanoparticle synthesis. Now, there was a lot of spinning sidebands, and it was kind of difficult to interpret that spectrum. So we then do a sideband separation experiment, in this case, a magic angle turning experiment. Linden's group has also done these types of experiments with past Pieta. So what this experiment gives us is an isotropic spectrum in the indirect dimension now. And then we can pull out rows that will show us the anisotropic sideband manifold for those different isotropic chemical shifts. So as we would expect, cadmium sulfide has negligible or 0 CSA because we have a symmetric cadmium atom. It's tetrahedrally coordinated by 4 sulfur atoms. The surface atoms, though, we're going to have 2 oxygens and 2 sulfurs. That breaks the symmetry of our tetrahedron and leads to an appreciable CSA. And then this impurity, we think, is octahedrally coordinated cadmium and also has negligible CSA. Now we can do some other experiments. This is a cadmium-113 spin diffusion experiment. So what we do here is we polarize those cadmium atoms on the surface, and then we watch how cadmium-113 spin diffusion can transport that polarization into the core signal. And so this experiment's nice because it really does confirm that we are seeing the signals from the surface species. We can also do cadmium-113 inadequate single quantum, double quantum correlation experiments. These are nice because we are using the 2-bond cadmium J couplings. So cadmiums that share a sulfur will be J coupled to one another. Those J couplings are about 125 hertz based upon the mixing time that we use in the inadequate experiment. And doing those types of experiments, we can also directly see the link between those surface and core cadmiums. This is new data that's unpublished and is something we're working on right now. So what I'm showing you here is some DNP enhanced NMR spectra of cadmium selenide nanoparticles. We've got carbon NMR on the left, the cadmium-113 NMR in the middle and selenium-77 on the far right. So this is for a series of ligand exchange particles. The reason that nanoparticle chemists do this is because you initially synthesize your particles using carboxylate ligands during the colloidal synthesis step, but these are not very good ligands for the particles. They tend to dissociate. You tend to get a lot of undercoordinated atoms, and when you first synthesize your particles, you don't get very good optical properties. So if you want to improve the optical properties, you can go through these ligand exchange reactions, put on chloride surface ligands and neutral phosphines, or you can change out the neutral phosphines for neutral amines. These are even better surface ligand. And so these particles will have much better emission and absorption properties. And now we can really follow these ligand exchange reactions very easily with the DNP. You can see the clear differences in the carbon NMR spectra, and then we can see really interesting changes in the cadmium and selenium NMR spectra. And we're trying to work this out and understand how we can actually determine the structure of the surface using this data. So that's something that's ongoing and has really been slowed by the shutdown of the lab recently. How am I doing on time, Kong?
It's already way past, but like,
Okay,
how many slides do you have?
I'll skip over the last part. I'll just say I can answer this in the question if anybody's interested.
I think the people will be.
I'll skip it. I'll just say I was going to talk a little bit about fast magic angle spinning and DNP combined, but
That's excellent.
For the questions. And I'd be happy to answer any questions. And again, I just want to thank all of the graduate students who did the work.
If you have anything you want to show on the fast mass and the DNP, I think like that would perhaps like interest the community a lot. Maybe you want to like talk briefly like on the last few minutes.
Sure. Yeah, I can do that. Okay. So yeah, I think everybody in the solid state NMR community is aware that proton detection and fast magic angle spinning have emerged as a powerful technique to enhance sensitivity. And this was really work that was first shown by Ishii and Tico, but lots of people have made contributions in this area. Mark's group has made some important contributions to using proton-detected experiments to look at surfaces. And so obviously there's interest in combining both DNP and fast MAS. Linden's group published a nice paper back in 2016 showing that enhancements don't really go down. Of course, this is on-off enhancement. This is not reflecting depolarization. But enhancements don't go down when we increase the MAS frequency. And then in some cases, you can also get increases in T2 prime. So what we've been doing in this most recent study that we're hoping to submit the manuscript soon is looking at combining fast MAS and proton detection. So I'm just showing here our 10 kilohertz cadmium-113 NMR spectrum of the cad sulfide and 31 kilohertz spectra obtained on a 1.3 millimeter DNP probe. So if we compare the absolute sensitivity, so that's going to be the signal to noise ratio of the cadmium spectra per the square root of the unit time, we see about a 4-fold loss in the cadmium sensitivity for these cadmium detected CPMG experiments. That's entirely expected because your 1.3 millimeter rotor has a much smaller sample volume than a 3.2 millimeter rotor. But it's only a factor 4 loss in sensitivity. And the nice thing about the faster magic angle spinning here for cadmium is because it has a very large chemical shift anisotropy, the faster MAS frequency can eliminate the sidebands and give you that isotropic spectrum, which you needed to perform an MAT experiment at the slower MAS frequency to get. So this actually does save you some time if you're interested in getting the isotropic spectrum. Now, if we try and do the proton-detected cadmium experiment with the ID HEC core type approach, we actually lose sensitivity. The reason for that is CPMG is very efficient in this system. We have a very long T2 prime. The other thing that holds back the indirect detection here is the fact that the CP is relatively inefficient. Your nearest proton is a couple angstroms away from the cadmium, so that leads to really low CP efficiency and prevents the proton-detected experiment from providing a net gain in the sensitivity. I'll just go through this quickly and say, if we go to a nucleus with a much lower gyromagnetic ratio, yttrium-89, these are yttrium-89 DNP sense experiments on yttrium oxide nanoparticles. Because yttrium-89 has a low gamma, it's about 20 times less than that of the proton, we would expect that there's going to be about a factor 90 potential improvement in sensitivity by doing a proton-detected experiment. And indeed, this is what we see. So if we compare the 3.2 millimeter yttrium-89 DNP-enhanced CPMAS spectrum to the 1.3 millimeter yttrium-89 detected CPMAS spectrum, we only see about a factor 2 loss in sensitivity. But now if we do the proton-detected yttrium-89 experiment with the ID het core pulse sequence, we can get a factor 8 net improvement in the sensitivity over the 3.2 millimeter rotor. So this is nice. You've really cut down on the amount of sample. You only need a couple milligrams of sample for the 1.3 millimeter rotor, and the proton detection really does provide good signal gains for these low gamma nuclei. And with that, I've taken up more than enough time. And again, I'll thank the people who did the work, and I'd be happy to answer any questions.
All right, thank you, Aaron, for your very interesting talks. So I will not ask any questions because there are already quite many of them in the Q&A. So I'll just go to the first one by Michael Hope. If you have unpaired electrons in the mixed selenites, does that not reduce the very long T1? Can we
yeah, it does. So for the ball milled sample and the annealed sample, we can actually reduce the delay that we use to acquire the spectra. So I think my student was able to actually get a spectrum with a 1 second delay. But the problem is you also get a big hit on the T2. And so that kind of makes it difficult. We've tried a couple times to do some faster magic angle spinning experiments. So using a 2.5 millimeter rotor to do 25 kilohertz MAS selenium experiments, and we still kind of fail to get reasonable magic angle spinning spectra. So I think the loss in the T2 maybe hurts you more than the reduction in the T1.
How much is the loss in the T2?
Well, we can't really see the signal under magic angle spinning. Under static, I'm under the impression we can maybe acquire echoes for, say, 10 or 20 milliseconds, but certainly not for seconds anymore.
Okay. All right. So next question from Daniel Lee. Do you attempt a CP MQMAS on the boron, maybe with DNP, to help resolve the overlapping sites?
Yeah, we tried to set that up, and we really struggled for some reason. It's something that we need to revisit. We're also doing some work on those systems on the 35 Tesla Tallahassee system. So the advantage of going to that is you can just get isotropic boron spectra without doing the MQMAS. So we're working on a manuscript for that. Hopefully that'll be out in a couple months.
Mm-hmm. And the next question from Jeffrey. The improved resolution of 14M with respect to 15M spectra is quite remarkable. Is it due to the second order isotopic quadrupole shift? Is that?
Yeah, that's exactly it. So when you do the N14 experiment, your peak position, this is done at a 9.4 Tesla magnet. So it's the second order quadrupole shift actually has a bigger effect on the peak position than the isotropic chemical shift. So that's what really helps to give better resolution for the nitrogen-14 in this case.
So they will be better at higher field?
Well, at higher field, I guess the resolution should be more or less the same. The second order powder patterns will scale inversely with the applied field,
exactly,
as will the second order chemical shift or quadrupole induced shift. So I think the resolution would stay the same actually.
Okay. Next question from Frederick. Under microwave irradiation, do you observe direct polarization of boron? If yes, have you characterized it?
We've done it, that experiment. We published it in a 2019 paper. It's probably in the SI. And I think we saw enhancements of like 10 or 20 for the direct boron DNP. One thing that really helped the boron experiments on the HBN is the boron T1 is actually extremely long in that material when it's not oxidized. So if you look at the kind of pristine material, you have a boron T1 of like 140 or 200 seconds at room temperature. So it's actually a really nice material to do direct boron DNP. I suspect that long T1 and the boron spin diffusion helps give you a reasonable DNP enhancement.
Okay. Next question from Snadis. Have you estimated the spin diffusion rate between the selenium?
Selenium, no, we haven't tried to estimate that yet. I think that's one of the issues that also prevents DNP from working in the mixed systems. So DNP probably works fairly well when you have the pure selenides, because each of those selenium atoms that make up the material is going to have the same chemical shift. When you go to the mixed materials, in addition to creating those radicals that help reduce the selenium T1, and in some cases destroy the radicals for the DNP, you're going to have a big distribution in the isotropic chemical shift. That's going to reduce the selenium peak overlap, and that's going to reduce the selenium spin diffusion rate.
Okay, next question from Raj. Is the first order quadrupolar coupling for 40N of HBN an issue for you to study?
No, so the bulk N14, the nitrogen CQ for the bulk sites in HBN are actually quite small. So the bulk site has a narrow peak. The CQ there, I think, is only like 200 kilohertz. These edge sites have quadrupole coupling constants, I think, between 1 and 2 megahertz. And those are pretty easy to study with HMQC techniques.
Okay, just like looking through the questions, I will take a few more. So like Nathan Barrow asked, for the hexaboron nitride, when you saw the tetrahedral before environment, do you know what could be charge balancing this? Is this a new overlook feature of the termination edge or preparation artifact? Can you look through a Q&A?
Yeah, I got the question.
Yeah.
Sure, I skipped over it. We've also modeled the edges and calculated the boron NMR spectra. So basically what we think has happened is you have some hydrolysis of the edge has occurred. So if we add an extra hydroxyl group to one of those boron sites that only had one hydroxyl group, that'll give us a 4-coordinate boron. Now that'll have negative charge. So then we just assume that it would be the other proton from the water that would be providing the charge balance. And so this is a stable structure according to plane wave DFT, and that would give you a 4-coordinate peak that would explain the spectrum that we see experimentally.
Okay, I mean, like, I would just take 2 more questions, and then there's this question that has a lot of discussion. And someone asked, like, can you use the unpaired electrons you produce by bond milling to do DNP rather than impregnate with an exogenous radical?
Stay tuned. So in the selenium, I don't think we can, but we found some other materials where we think we can.
Mm-hmm. I think you show an EPR spectrum where you estimate the radical concentration to be 7 millimolar or 9 millimolar.
70. Yeah, so wow. These are actually quite concentrated. So this is not the best figure because the scale is changing when you compare these different ones.
Mm-hmm.
So when you initially mill it, you have this extremely broad signal, which I'm assuming must be G anisotropy due to the selenium or molybdenum or tungsten. And then when you anneal it, that broad background signal goes away and you're left with just that sharp signal in the middle. And that's what we see. But even this one still has a pretty big G anisotropy. We've also done some work on irradiated solids. And we basically see when you get these radicals that have very large G anisotropy, they're just not compatible with CW DNP. You know, I think in the future, your work with Bob and the things that Xander and Song-Yi are doing, you know, maybe if we can get coherent DNP to work, pulse DNP, then we can start using these really broad radicals to actually polarize nuclei.
All right, I will say stay tuned. Okay, maybe I'll just take the last question. Can you comment on the sample preparation for hexaboron nitride sample with solid matrix with TechPol DUTCE?
Yeah, we just use the TechPol tetrachloroethane and just impregnate the materials. So, you know, you take 20 or 30 milligrams of powdered material and then 10 or 20 microliters of the pre-made radical solution, and radical concentration is 12 to 16 millimolar.
Yeah, I think like we are way beyond the time, and so thank you for staying tuned and listening to our session. If you have more questions, feel free to write to Aaron. And yeah, thank you for your very nice talks and very interesting show of like DNP applications on materials. Bob, you want to say something?
Nothing particular, except that both talks were really quite nice and enjoyable today. Great examples of what NMR, DNP, and solid-state NMR can do for materials research. So let's thank both Aaron and Evan very much for these presentations. And Kong-Hu is on tab for next week. I
thought you are. No, I'm just joking. So next week we have our good friend Shita Jain, so who's doing a postdoc with Song-Yi Han now, and then we have Ilya Kuprov, who's going to tell us about spins. Southampton, yeah.
Okay. So we will see everyone next week then. All right, same time, same place.
In a space. All right. Bye.
Bye.